Hey students! Welcome to Thermodynamics, the study of energy changes in chemical reactions. In 20 minutes we will master the first law, internal energy, enthalpy, Hess's law, entropy, the second law, Gibbs free energy, and predicting spontaneity. Plus, we'll solve 3 NEB-style numericals on Hess's law and Gibbs energy. This unit builds on your Class 11 basics. Let us go. Hello students! In thermodynamics, let's start with some fundamental terms. We divide the universe into 2 parts. The system is the specific part we're studying, for example a chemical reaction. Everything outside the system is called the surroundings. There are 3 types of systems. An open system can exchange both matter and energy, like a beaker of hot water. A closed system allows only energy exchange, such as a sealed flask of gas. And an isolated system exchanges neither. A good example is a thermos. We also classify thermodynamic properties. State functions depend only on the current state, not the path taken. These include internal energy, enthalpy, and pressure. Conversely, path functions like heat and work depend on the process. Finally, extensive properties like mass and volume depend on the amount of substance, whereas intensive properties like temperature and density do not. Now let's discuss the first law of thermodynamics. It states that energy can neither be created nor destroyed, only transformed from one form to another. Its mathematical statement is delta U equals Q plus W. Here, delta U is the change in the system's internal energy, Q is the heat exchanged, and W is the work done. We must be very careful with signs. According to IUPAC convention, Q is positive when heat is absorbed by the system, and it's negative when it's released. Similarly, W is positive when work is done on the system, like compressing a gas, and it's negative when it's done by the system, such as a gas expanding. For the specific case of an ideal gas expanding against a constant external pressure, the work done is given by the formula W equals minus P times delta V. Next, we introduce a crucial concept called enthalpy. Enthalpy, symbolized by H, is defined as H equals U plus PV, where U is internal energy, P is pressure, and V is volume. Like internal energy, it is a state function. Now, why is enthalpy so important? At constant pressure, the heat exchanged in a process is exactly equal to the change in enthalpy, delta H. This is incredibly useful because most lab experiments are done in open containers at constant atmospheric pressure. The relationship between them is delta H equals delta U plus P times delta V. For reactions involving gases, a more convenient form is delta H equals delta U plus delta N subscript GRT, where delta N subscript G is the change in moles of gas products minus reactants. Let's explore some specific types of enthalpy changes. First is the standard enthalpy of formation, symbolized as delta H standard F. This is the heat change when 1 mole of a compound is formed from its elements in their standard states. Next, the enthalpy of combustion is the heat released when 1 mole of a substance burns completely in oxygen. The enthalpy of neutralization is another key type. For a strong acid and strong base, this has a nearly constant value of about minus 57.1 kilojoules per mole. Many other types exist, such as the enthalpy of solution, atomization, and bond dissociation, each corresponding to a specific process. Hello students! Today, we're discussing Hess's law of constant heat summation. This fundamental principle states that the total enthalpy change of a reaction is the same, whether the reaction occurs in one single step or in several sequential steps. Why is this true? It's because enthalpy, which we represent with the letter H, is a state function. This means it's path independent, it only depends on the initial and final states, not how you get there. This law is incredibly useful for calculating the enthalpy change for reactions that are difficult to measure directly in a lab. A classic example is the formation of carbon monoxide from carbon and oxygen. It's hard to stop the reaction from also forming carbon dioxide. So, we use an indirect route. We can measure the enthalpy for carbon reacting to form carbon dioxide and also the enthalpy for carbon monoxide reacting to form carbon dioxide. Then, the enthalpy change for carbon to carbon monoxide simply equals the enthalpy of C to CO2 minus the enthalpy of CO to CO2. Next, let's talk about a concept called entropy, symbolized by the letter F. Entropy is a measure of the disorder, randomness, or chaos within a system. Its units are typically joules per Kelvin per mole. A key point is that for any spontaneous process occurring in an isolated system, the entropy always increases. The change in entropy, delta S, can be calculated as the reversible heat transfer, Q reversible, divided by the absolute temperature, T. This is particularly useful for phase changes. For example, the entropy of vaporization equals the enthalpy of vaporization divided by the boiling temperature in Kelvin. Thinking about states of matter, solids have the lowest entropy because their particles are in a fixed, ordered lattice. Liquids are more disordered, and gases, with their rapidly moving, far-apart particles, have the highest entropy. In general, entropy increases with rising temperature when a solid dissolves or when a gas expands into a larger volume. The second law of thermodynamics is one of the most profound laws in science. It essentially tells us the direction that natural processes take. There are several ways to state it. The Clausius statement says that heat flows naturally from a hotter object to a colder one, and never spontaneously in the reverse direction without external work. The Kelvin statement says it's impossible for any engine to convert all the heat it receives into useful work. Some heat is always lost. For us chemists, the most useful version is the entropy form. This states that the total entropy of an isolated system always increases over time for any spontaneous process. Mathematically, we say that delta S of the universe, which equals delta S of the system plus delta S of the surroundings, must be greater than 0 for a process to be spontaneous. This is why the universe tends towards greater disorder. So, how do we combine enthalpy and entropy to predict if a reaction will happen? We use Gibbs free energy, represented by G. It's a state function defined as G equals H minus Ts, where T is the absolute temperature. The change in Gibbs free energy is given by what might be the most important equation in chemical thermodynamics, delta G equals delta H minus T times delta S. This equation is our key to spontaneity. If delta G is less than 0, the process is spontaneous, and we call it exergonic. If delta G equals 0, the system is at equilibrium. And if delta G is greater than 0, the process is non-spontaneous, or endergonic. Physically, delta G represents the maximum amount of non-expansion work a system can do. Hello students, let's tackle a thermodynamics numerical. Here's the question: for a reaction delta H equals minus 100 kilojoules per mole, delta S equals minus 150 joules per Kelvin per mole, temperature is 300 Kelvin. Calculate delta G and predict spontaneity. Alright, first, let's list our given values. Delta H is minus 100 kilojoules per mole. Delta S is minus 150 joules per Kelvin per mole. And T is 300 Kelvin. The first crucial step is to ensure our units are consistent. We'll convert delta S to kilojoules by dividing by 1000. This gives us delta S equals minus 0.150 kilojoules per Kelvin per mole. Now, we apply the Gibbs equation, delta G equals delta H minus T times delta S. Let's substitute our values, delta G equals minus 100 minus 300 times minus 0.150. The calculation simplifies to delta G equals minus 100 plus 45. This gives our final answer, delta G equals minus 55 kilojoules per mole. Finally, to predict spontaneity, we look at the sign of delta G. Since delta G is negative, the reaction is spontaneous at 300 Kelvin. Hello students. Let's explore how temperature affects whether a reaction is spontaneous. We use the Gibbs-Helmholtz equation, delta G equals delta H minus T, delta S. The spontaneity depends on the signs of enthalpy change, delta H, and entropy change, delta S. This gives us 4 possible cases. Case 1, when delta H is negative and delta S is positive, the reaction is always spontaneous at all temperatures because delta G will always be negative. Case 2, if delta H is positive and delta S is negative, the reaction is never spontaneous. Case 3, when both delta H and delta S are negative, the reaction is spontaneous only at low temperatures. And finally, case 4, when both delta H and delta S are positive, the reaction becomes spontaneous only at high temperatures. The temperature at which the reaction switches between spontaneous and non-spontaneous is called the transition temperature, found by setting delta G to 0, which gives T equals delta H divided by delta S. Now, let's connect thermodynamics to chemical equilibrium. The change in Gibbs free energy for any non-standard condition is given by delta G equals delta G naught plus RT natural log of Q, where Q is the reaction quotient. The most important point is at equilibrium. At equilibrium, the reaction has no further net tendency to change, so delta G equals 0 and the reaction quotient Q becomes the equilibrium constant, K. Substituting these into our equation, we get 0 equals delta G naught plus RT natural log of K. Rearranging this gives us the crucial relationship, delta G naught equals minus RT natural log of K. This equation tells us three things. If delta G naught is negative, K must be greater than 1, meaning products are favored at equilibrium. If delta G naught is 0, K equals 1. And if delta G naught is positive, K is less than 1, so reactants are favored. The third law of thermodynamics provides a fundamental reference point for entropy. It states that the entropy of a perfect crystalline substance at absolute 0 or 0 Kelvin is exactly 0. At this temperature, all atomic motion ceases and there is only one possible arrangement for the atoms in the crystal lattice, meaning there is no disorder. This absolute 0 point for entropy allows us to calculate the absolute entropy of a substance at any other temperature. We can do this using the formula S equals the integral of Cp divided by T dt from 0 to the final temperature T. This is incredibly useful because we can then find the standard entropy change for any reaction, delta S naught, by using the tabulated standard absolute entropies of reactants and products. Finally, let's see how these principles apply in the real world. In electrochemistry, the spontaneity of a battery's reaction is related to its cell potential by the equation delta G equals minus NFE. In our own bodies, complex metabolic processes are driven by the energy released from ATP hydrolysis. The delta G for this reaction is about minus 30.5 kilojoules per mole. Industrially, the Haber process for making ammonia is fascinating. Thermodynamically, it's favored at low temperatures, but the reaction is too slow. So, a compromise of moderate temperature and a catalyst is used. Even your refrigerator is a thermodynamic machine. It's essentially a heat engine in reverse, using work input to move heat from a cold space to a warmer one, which is a non-spontaneous process. Hello everyone. Let's solve a classic Hess's law problem. We need to find the enthalpy change for the reaction, C plus half O2 gives CO. We are given two equations. Equation 1, C plus O2 gives CO2 with delta H at minus 394 kilojoules per mole. Equation 2, CO plus half O2 gives CO2 with delta H at minus 283 kilojoules per mole. To get our target equation, we need to manipulate these. Notice that carbon monoxide, CO, is a product in our target, but a reactant in equation 2. So, we must reverse equation 2. When we reverse it, the sign of delta H also reverses, becoming positive 2E. Now, let's add equation 1 and the reversed equation 2. C plus O2 plus CO2 gives CO2 plus CO plus half O2. The CO2 cancels out. The O2 simplifies to half O2 on the reactant side. This gives our target equation. The final step is to add the corresponding delta H values, minus 394 plus 283. The result for the enthalpy change is minus 111 kilojoules per mole. All right, for our next problem, let's calculate an equilibrium constant, K. We are given that delta G naught is minus 22.85 kilojoules per mole at 288 Kelvin. The fundamental equation we'll use is delta G naught equals minus RT ln K. To find K, we first rearrange it, ln K equals minus delta G naught divided by RT. A crucial step is unit consistency. We must convert delta G naught to joules, so it becomes minus 22.50 joules per mole. Now, let's plug in the values. ln K equals minus 22.80, all divided by 8.314 times 298. The denominator is about 2478. So, ln K is 22.80 divided by 2478, which equals approximately 9.22. To get K, we take the antilogarithm. K equals e to the power of 9.22. This gives us a very large value, approximately 10 to the power of 4. This large value for K means the products are strongly favored at equilibrium. Alright class, let's quickly recap thermodynamics. So to summarize, everything starts with the first law of thermodynamics, which is a statement of energy conservation. Remember this key formula, delta U equals Q plus W, where U is internal energy. Next we have enthalpy, delta H. For reactions involving gases, the crucial relationship is delta H equals delta U plus delta nRT. Don't forget Hess's law for calculating enthalpy change in steps. Finally, for spontaneity, we have Gibbs free energy. The master equation is delta G equals delta H minus T, delta S. And to connect it to equilibrium, remember that delta G naught equals minus RT natural log K. These are the absolute must-knows. Now for exam tips. NEB loves to test a few things repeatedly. First, watch your signs. Remember, work done by the system is negative. That's a common trap. Second, units are critical. When using the delta H equation, make sure your R value, 8.314, is in joules to match your energy units. Memorize the Gibbs free energy equation. Questions on spontaneity are guaranteed. A time saver for Hess's law is to work backwards from the target equation. And finally, always check if the temperature is in Kelvin. You've got this. Review these key areas, practice the numericals, and you will do great. And that's a wrap on thermodynamics. Congratulations on making it through this crucial unit. Always remember the Gibbs free energy equation, delta G equals delta H minus T delta S, which tells you if a reaction is spontaneous. If this video helped you, please give it a like and subscribe. Drop a comment for the next chapter you'd like to see. Coming up next, we'll dive into Unit 5 Electrochemistry. Stay tuned.